Hello everyone, I'm going to present a talk about dark matter mixed neutron stars. This work was made in collaboration with Alexei Ionitsky and Elydia Loksh. Despite the existence of many dark matter candidates, the nature of dark matter still remains unclear. And in this context, astrophysics provides means for constraining properties of dark matter particles from their impact on astrophysical objects. And neutron stars are good laboratories for it, as they may trap dark matter inside the star. As you can see from this figure, the mass-radius relation for neutron star described by the selected equation of state shows a decrease both in mass and radius due to the presence of dark matter. For example, let's take a look on this blue solid curve, which corresponds to MSY equation of state. And we see that after adding 5% of dark matter, we see a decrease of the maximum mass up to 2.5 solar mass, and as well we see a decrease of the radius of the star. And another effect of dark matter is related to its imprint on the gravitational wave waveform. Dark matter cores may produce a supplementary peak in the characteristic gravitational wave spectrum of neutron star merger, which can be clearly distinguished from the features induced by the baryon component. So, for example, for symmetric system, we can see F1, F2, and F3. These are three peaks related to baryon matter component. But we also see a new peak which appears due to the presence of dark matter. And at the same time, in very asymmetric system, we see exactly the same situation. We see F1, F2, and F3, three peaks related to baryon matter component, and we see two new peaks related to dark matter component. And another constraint on dark matter particles comes from the thermal evolution of neutron stars. So cooling simulation of neutron stars and further comparison of this simulation with experimental data of X-ray emitting neutron star can shed light on the properties of dark matter particles, on the amount of dark matter inside the neutron star, as well as the coupling constant of dark matter particles. So in these papers, it was shown how the existence of axions inside the dark matters, existence of axions inside the neutron stars led to changes on the surface temperature of the stars. And as you can see, this effect is different for different coupling constant of axions. So in our work, we focused on the effect of dark matter on the properties of neutron stars, and in particular on their on the ability of reaching two solar mass limit. So far, we know two neutron stars with masses above 2 solar mass. And despite the big uncertainties in the equation of state and the internal structure of the neutron stars, we know that the maximum predicted mass of the neutron star should be at least 2 solar mass. So in this study, the dark matter was treated in a very simplified way as relativistic Fermi gas of non-interacting particles with spin 1/2. And usually in the literature, this type of dark matter is referred as a symmetric dark matter. Baryon matter component was described with the equation of state with induced surface tension. This equation of state reproduces nuclear matter ground state properties, proton flow constraint, heavy ion collision data astrophysical observation, as well as the tidal deformability constraints. If you would like to take a look on the equation of state, please follow these two papers. The interaction between the baryon matter and dark matter were neglected. We considered only that they couple through gravity, and in this case, the energy momentum tensors conserved separately. It means that we can split the Tolman-Gamow-Volkel equation into two. The one will be is for baryon matter. The second one is for dark matter. As you can see here in the first brackets, we have energy density and the pressure of purely baryon matter, and the second it's energy density and the pressure of dark matter. And the second bracket, we have a total mass, which is the sum of baryon component and the dark matter component. And the pressure also corresponds to the total pressure, which is the sum of the pressures of two partial pressures of two components. And the fraction of dark matter inside the star would describe as the mass of dark matter component divided by the total mass of the star. So on this slide, you can see the mass radius diagrams for two cases, for very low mass dark matter particle and for heavy dark matter particle on the right. You see that for very light dark matter particle, the increase of the fraction of dark matter leads to also to increase of the maximum mass. It means that for any fraction of dark matter, we almost all the time in agreement with two solar mass constraint, which is not the case for heavy dark matter particle. For example, for a 1 GeV particle, we see that increase of the fraction of dark matter leads to decrease of the maximum mass. And the limiting case, we have 3.3% that corresponds to this red curve. It's a limiting case when we still in agreement with two solar mass constraint and all the fractions above this value will be in contradiction with two solar mass constraint. To understand why it's the case, why we have so different behavior for low and heavy dark matter particles, we plotted the energy density profile for both components separately. And we saw that the baryon matter component, which is depicted in blue here, vanishes at around 10 kilometers, at the size of the star. And at the same time, the dark matter component, which is depicted in black here, continues for much bigger distances. For example, at 0.3%, it equals more or less the radius of the baryon component. And at already 1%, it's twice larger than the baryon star. And at 3% of dark matter, the radius of dark matter component equals to 135 kilometers, which makes us to conclude that the light dark matter particles tend to create very dilute and extended halo of dark matter around the baryon star, which is not the case for the heavy dark matter particle. For example, if we'll take a look on the right, we have a plot for the mass equal 10 GeV. We see that baryon component vanishes at 10 kilometers, the visible size of the star, and the dark matter component vanishes at around 100 meters, which makes us to conclude that heavy dark matter particles create very dense core inside the neutron star, while the low mass particle create extended halos around the star. So we decided to find out the limiting case when we still, for any fractions of dark matter, are in agreement with two solar mass constraints. So we plotted a figure maximum mass as a function of the fraction of dark matter for three different values of mass dark matter particles: for 100 MeV, for 174 MeV, and for 1 GeV. For 100 MeV, as I said before, we all the time in agreement with two solar mass constraints. So we have a little bit of decrease of the maximum mass, and again start to rise again. And for 174 MeV, it's a limiting case when we see a decrease of the maximum mass, then it reaches the minimum at exactly two solar mass and then start to rise again. So it means that for 174 GeV, for any fractions of dark matter, we're still in agreement with two solar mass constraints. While for a little bit heavier stars, for example, for 1 GeV, we above two solar mass up to only for some certain values of fractions up to 3 GeV, 3% here. And for the fractions above 3%, we are in contradiction with two solar mass constraints. Okay, we know that two solar mass constraint haven't been violated. So let's fix this value, two solar mass, and we plotted this like a black curve. All the fractions of dark matter and the masses of dark matter that lays in the region below this curve, they correspond to a allowed region of parameters when the star will always have a maximum mass greater than two solar masses. In the region above this black curve, we have a region of not allowed parameters when we cannot reproduce two solar mass neutron star. If we'll take a look on a very light star, like 100 MeV, we see that for any fraction of dark matter, we can reproduce two solar mass constraint. It means that this black curve goes up. And the limiting case, as I showed on the previous plot on 174 MeV, our behavior change and we reach exactly two solar mass. Then for heavier dark matter particles, we can have a two solar mass up to some certain values of the fractions. That's why we have such changes of the behavior of this black curve. At the same time, we see that we have a big region of parameters of fractions and the mass. Can we estimate the fraction of dark matter inside the star? The first attempt was to use the Navarro-Frank-White distribution and a Nasto distribution for dark matter, and for baryon matter use a stellar disk structure. We pick up two neutron stars with masses above two solar masses. We know the distance of these two stars from the galaxy center, and from this we can calculate the fraction of dark matter in the surrounding media around the star. And from Navarro-Frank-White distribution, we got 1.6 and 1.35% corresponding. For a Nasto distribution, we got 1.35 and 1.12%. And we plotted these two values as a horizontal line, the red one and the blue one. So this fraction F chi star corresponds to the fraction in the surrounding media. But the fraction of dark matter inside the neutron star will depend on the different factors, for example, on the accretion rate of dark matter during the different life stages of neutron star, as well as the cross-section of dark matter and baryon matter. So how can we estimate this accretion rate on the neutron star? We know some stages of star evolution from the progenitor to neutron star. So we know that during the star formation stage, the baryon matter and dark matter can be mixed inside, and after contracting and make a progenitor star, dark matter will be trapped inside this cloud, and it will undergo a scattering process with baryons, will start to lose kinetic energy and will be thermalized later on. When the star enters to the main sequence, due to the big gravitational potential, there will be big accretion rate, and we can estimate that for the most central parts of our galaxy, the amount of accreted dark matter can be between 10 to the minus 5 and 10 to the minus 9 solar masses. Then during the stage of supernova explosion and formation of proto-neutron star, we can say that newly born neutron star will be surrounded by the dense cloud of dark matter with a temperature and radius that corresponds to the previous stage, to the main sequence star stage. And at the same time, supernova explosion can lead to production of new dark matter inside the star. And mostly this dark matter will be trapped inside the star. And then the last stage, the equilibrated neutron star, also will continue to accrete dark matter. And depending on the distance from the galaxy center and the cross-section of the baryon matter, the amount of accreted dark matter material is in the range between 10 to the minus 8 up to 10 to the minus 5 solar masses. So when we sum up all the accumulation regimes and the amount of dark matter accumulated during all the stages, we can conclude that the amount of accreted material in the close proximity to the galaxy center is around 0.01%. And if we'll take a look on the cross section of this horizontal line in our black curve, we can conclude that detection of a two solar mass neutron star that lays on this black curve in the galaxy center, in the close proximity from the galaxy center, will give us upper constraint on the dark matter particle equals to 60 GeV. And of course, the more precise measurements of the dark matter accumulation regimes inside the neutron star will put more tight constraint on the on this value and will help us to place this horizontal line more precisely. And after that, in the cross of this horizontal line with our black curve, we can estimate the maximum mass of dark matter particles. So I will go to my conclusions. Using the observational fact of existence of two heaviest known neutron stars with the masses exceeding 2 solar ones, we present an allowable range of masses and fractions of dark matter particles. We demonstrate that dark matter lighter than 200 MeV can create an extended halo around the neutron star, leading not to decrease but to increase of the total mass. By using recent results on the distribution of dark matter in our galaxy, we made an estimation of the fraction of dark matter in neutron stars in the close proximity of the galaxy center. And the measurements of two solar mass neutron stars in galaxy center will impose an upper constraint on the mass of dark matter particles, which is around 60 GeV. And of course, we are looking forward for the future and the present radio telescopes and X-ray missions that are planning to increase the number of detected neutron stars in the galaxy center, as well as to make more better measurements of the masses of the neutron star. And using both results, we can put even more tight constraint on the mass of dark matter particles. Thank you for your attention.